Hello, my dear students. I'm Shweta Roslin, working as an assistant mistress in Nirmala High School, VV Mohalla, Mysore. Today, let us know about the electromagnetic induction. I hope it's useful and informative. Before going to start, the exact definition of electromagnetic induction, here I have taken a coil, a bulb, a meter to detect the current in the circuit. Usually we take a galvanometer. Then I have a magnet. You can observe that the coil, bulb and a meter, that is galvanometer, are connected through the connecting wires. Let us start this class with an activity. Dear children, be attentive now. First, I have taken a magnet. Now in this magnet, can you observe two poles? North pole and a south pole. Every magnet is being surrounded by a magnetic field lines. Usually the magnetic field lines will move from north towards the south. I'll show you the magnetic field lines. Can you observe now? Yes. The magnetic field lines will emerge from north pole and it will merge towards the south. Now I'll take off this magnetic field lines. I'll come back to it later. Now, if I bring this magnet inside the coil, then they say that the current is induced in the coil. If I bring the magnet, remember, only I am bringing the magnet but not any of the external source. But you should also note a point that the coil what I have taken is a good conductor. All these observations are first demonstrated by a physicist, that is Michael Faraday. Let us see some of the observations made by him. When I am keeping the magnet as well as the coil apart, that means I am not taking the magnet inside the coil, then can you observe any changes in the electric bulb as well as the galvanometer? No. There is no change in the electric bulb as well as a galvanometer. Now, if suppose I bring north pole of the magnet inside the coil, just see, is there any change in the electric bulb now? Yes, the bulb glows and the galvanometer shows deflection. Yes, that means when the magnet is moving inside and coming out of the coil, the bulb glows. That means the movement of the magnet in the coil induces the electric current. As I have said, galvanometer is a instrument to detect the presence of current. It will show deflection only when there is a electric current induced in the circuit. Now as I am bringing the north pole, you have to observe where this needle deflects, whether it is deflecting towards the right or towards the left. Now as I bring the north pole of the magnet inside the coil, deflection is towards the left. Did you observe? Once again I will bring it. Just observe. As I am bringing the north pole of the magnet towards the coil, can you observe? Yes, the deflection was towards the left. Now the same magnet I am bringing out of the coil, then the deflection is towards the right. Once again it is towards the right. Now you have understood why the induced current is being there in the circuit. It is only because of the movement of the magnet. As I have said earlier, the magnet is surrounded by a magnetic field. Now, what I'll do is, instead of moving the magnet, I'll keep the magnet just inside the coil and I won't move it again. That means I'll keep this magnet as a stationary object inside the coil. Do you observe any change in the bulb as well as the galvanometer? You can observe the bulb doesn't glow and the galvanometer is not showing any deflection. That means the stationary magnet will not induce electric current in the circuit. Remember, the current is induced only when there is change in the magnetic field around a current carrying conductor. Now, let us check. If suppose I change the poles of the magnet, here I have got north and there I have got south. If I change it, if I reverse the poles of the magnet, instead of bringing the north pole towards the coil, I'll just bring south. I have changed. Can you see now? South pole and here it is north pole. I have brought this south pole, so I am bringing this near the coil. Can you see? So then also I can see the deflection in the galvanometer and the bulb glows. Yes, but observe carefully the deflections in the galvanometer. The galvanometer, now the deflection is shown towards the right. Earlier where it was? Earlier it was towards the left. Now it is towards the right. Now observe the same magnet. I am not changing the magnet here, but I have only changed the poles of the magnet. So now I'll bring it out. When I bring it out, where does the deflection show? It was shown towards the left side. Earlier it was towards the right. Now what it indicates? As I've said earlier, the magnet is surrounded by a magnetic field. When I change the poles of the magnet, I have changed the directions of the magnetic field. Once I change the directions of the magnetic field, automatically the direction of the induced current also changes. Now, what I'll do is, let us come back to the magnetic field lines. So, here I have got a magnetic field lines. So, I'll bring this magnetic field lines and I am going to change the poles of the magnet as it was earlier, that is north and south. Now, I'll keep the magnet as well as coil in such a way that the coil is surrounded by the magnetic field lines, but the poles are away from the coil. Now, instead of bringing the magnet in and out of the coil, I'll just shake it slightly. Can you observe any change in the galvanometer now? Yes. And see the bulb also? Yes. The bulb glows feebly, very slight, and the deflections are also very little. That means, though the coil is surrounded by the magnetic field lines, you have to understand the characteristics of the magnetic field lines first. Because the magnetic field lines strength is more towards the pole than away from the pole. As you move away from the pole, the strength of the magnetic field decreases. Though the coil is surrounded by the magnetic field, the strength is less. When the magnetic field strength is less, the current induced is also lesser. That means the amount of current produced is also lesser. That means you have to understand the poles, near the poles, the magnetic field strength is more. We call this area that is near the pole as a magnetic flux. Magnetic flux is nothing but it is the area in which the magnetic field strength is more. Now if suppose I bring this magnetic field, the magnetic flux inside the coil and out of the coil, can you see how the bulb is glowing and how the deflections are shown? Yes. That means as the magnetic field strength increases, the amount of induced current produced is also increases. When the magnetic field strength decreases, then the amount of induced current also decreases. Now, the next, we'll move on to the next bit, that is, I'll take off the magnetic field lines now. If suppose, can you observe the coil now? The coil has got how many number of turns? It has got 4 number of turns. Now instead of this coil, I'll consider one more coil having lesser number of turns. Along with that, I'll attach one more coil having lesser number of turns. Here I've got 2 and the earlier case I have got 4 turns. Now what we have to check is how the number of turns of the coil influences the induced EMF or induced current in the circuit. Now I am going to take this magnet to the earlier coil what we have considered. Just see, moving in and out of the coil, the bulb glows and the deflection in the galvanometer. Can you observe the deflection? The needle of the galvanometer is deflected to extremes on either side. It is touching the extremes on either side. These two extremes have been covered when the number of turns are more. The same magnet I am moving inside a coil having lesser number of turns. Can you see? As the number of turns is lesser, observe the magnetic needle in the galvanometer. So in the galvanometer, the deflections, though there is a deflection, but it is not touching the extremes on either side. And also the bulb is glowing, but it is not so brighter than the earlier case. So what we have understood from this, children? So we have understood that as the number of turns of the coil increases, the induced current or induced EMF in the circuit also increases. As the number of turns in the coil decreases, then the amount of induced EMF also decreases. Then at last, let us come back to the our 4-turn coil. Now, one more point you have to note here is the speed in which the magnet is moved inside and outside the coil. If I want the continuous supply of induced EMF inside the circuit, then I have to move this magnet with a greater speed. As the speed of moving the magnet in and out of the coil increases, then there is a production of electric current continuously, or the EMF is induced continuously. The same magnet is moving inside and out of the coil with a lesser speed, that is with a slow motion. Then can you observe the bulb glows and automatically when it rests, the magnet rests, the bulb turns off and there is no deflection in the galvanometer. That means when there is the speed of the movement of the magnet is lesser, then there is no continuous supply of induced current. That means as the speed of the movement of the magnet increases, then there is a continuity in the inducing of the electric current in the circuit. Now, at last, observing all these factors, first we saw how the North Pole, that is exactly about the field lines, how the change in the magnetic field around a current carrying conductor changes the deflections in the galvanometer as well as the bulb. That means the induced current is produced in the circuit. And also we saw when we change the poles of the magnet, that is south to north pole, then also we saw how the deflections in the galvanometer are reversed. That means as we change the direction of the magnetic field, the induced EMF direction also changes. And also we saw as the number of turns increases, then the amount of induced current produced also increases. And also we saw the magnetic field strength is more, then the amount of induced current produced is also more. At last, observing all these factors, we can define electromagnetic induction. Electromagnetic induction is nothing but change in the magnetic field around a current carrying conductor. Around a current carrying conductor induces an electric current. This is nothing but electromagnetic induction, and this itself is the statement for Faraday's first law. So I hope children you have understood it. Thank you all for watching this. Stay at home, be safe, and keep in touch with your studies. Thank you, children.